weekend and happy Tuesday. Today, we will continue on with our discussion of feature selection, and we'll look at methods that are amenable to so-called non-linear geometries in your data. And so the reading in support of this are the following links. There's one on Isomap, which is the method of interest that we'll be talking about today. You'll need to also look at a refresher on Eigen Decomposition, look at this entry concerning what a centering matrix is and what it does, as well as this video on Dijkstra's algorithm for computing the shortest path of distances. So where we last left off, we talked about PCA, and we motivated PCA looking at a physical example concerning a spring mass damper system whose motion path is measured by 3 different cameras, A, B, and C. And so in this, we were after uncovering from our sensor measurements the X and Y position from the perspective of each camera for this mass over time, i.e. the dynamics. But the problem was that we only had access to the sensor measurements. We don't know what the true dynamics are, which in this case is the X dimension in R3. But we don't know this. All we know is what we measure. And so we sought out through a transformation to find what the best direction is that most faithfully encodes or represents the dynamics of the system. And so for PCA, we took our data, put it in a design matrix, and we enterprised through a transformation P to find a new representation Y that had desirable properties. And so our transformation was a linear transformation. That linear part is very important because it makes it easier to solve for. We said Y equals PX. The new version of our data, each data point in the columns of X, are going to be the columns of Y. And so now we have a linear change of basis, and we seek out to specify what that transformation P is. And so we looked at this idea of covariance as describing the redundancy in measurement types. And we said that the off-diagonal terms, the covariances, talk about redundancy. If they're large, that means the 2 feature or measurement types are highly redundant. If the off-diagonal terms are small, we said those measurement types have low redundancy. Likewise, we wanted to maximize the signal-to-noise ratio, and signal-to-noise ratio was the proportion of the variance of the signal of interest divided by things that are not signal. And in maximizing this signal-to-noise ratio, that means we want to maximize the variance of the largest, in the direction of the largest variance observed for our system. And so in that, we want a special pathological covariance matrix, one where the diagonal elements are maximized and the off-diagonal elements are 0. So when we compute our transformation P, we want P to transform X such that the covariance in the new representation Y has a diagonalized form. And so with this, we went through a series of transformations, and we validated that if you choose as the rows of P the eigenvectors of the outer product of the original representation X, you absolutely get a resulting representation Y such that the covariance of that new representation is diagonalized, and we prove that mathematically. So we talk about feature selection, and the focus with PCA is in linear methods. And we said these linear methods make it easier to solve, but not all data that you encounter is going to be linear. So let's explore this idea a little bit more. Again, we can construct features through this phi function, some statistic over the original input representation. And in doing so, we can get desirable properties to make it easier to learn and compare data in feature space. And we talked about things like separation and noise, but the focus today is going to be on non-linearity and how we deal with this. And so let's consider nonlinearity. When we think about nonlinearity, there are certain types of phenomena that underlie the data that you see as expressed through features. If you think about photon energy, and let's say you're measuring photon energy, and those are your features at different wavelengths, photon energy is a result of electrons jumping valency levels because you inject energy, like you ablate some substance with a laser, pulse a laser. And so those electrons get excited and they jump energy levels. And then when you stop pulsing that laser, that energy is dissipated, they return back to rest, and in doing so, they release photon energy. And so this idea, this jumping of energy levels and returning back to rest for the electrons, that's a highly nonlinear process. And so features that you measure that arise from this are going to have nonlinear qualities associated with it. And so that just suggests that if you're going to do feature selection based on such a data set derived from this process, that you're better off looking at something that can better represent nonlinear phenomena. Likewise, let's take a look at a robot mechanism. Now, a robot mechanism has a bunch of joints. In this particular case, these are so-called revolute joints. They rotate about an axis. And when we look at the change in the angle associated with each joint, so here's one joint that rotates about this axis. Here's another joint, it can rotate about that axis, and so forth. I'm going to draw it in planar form. So here we have a two revolute joint mechanism. We have our first joint, and that joint can be represented as angle theta 1. And then we have another joint that can be at angle theta 2 with respect to the first joint. Now, if we look at the angular velocity of the joints, theta 1 dot and theta 2 dot, there's a nonlinear relationship between the angular velocity of the first joint and the second joint versus the position, change in position, x dot, y dot of the end effector, the position space of the end effector. And now for a mechanism depicted here, this is the Canova robot manipulator, a robot arm. It's even more complex because here we can rotate about this axis or about these following axes here, and this wrist can also rotate. And so when we think about the relationship between the angular velocity of the endpoint, the end effector, and the angular velocity as the joints, that's a nonlinear relationship. So any measurement or feature that you'd use to represent the velocity of this end effector's position, that's going to be nonlinear. So you probably want to do feature selection using a method that acknowledges that there is nonlinearity in the data. Lastly, let's take a look at this image. We have two images. One is a wide area image in frame A, and in frame C, that's a zoomed in version. It's the same scene. The camera's in the same position. You just zoom in, so you're changing the focal length for that camera. Now, of course, when you do that, certain pixels in the image, in the original image, will flee the image, so they'll disappear. Other new pixels that you didn't see will now enter the image. And so here we see new pixels have entered the image, existing pixels have fled the image, as well as some pixels that were there, like this flagpole, they remained there, but they changed a little bit in their appearance. And so this process is certainly nonlinear when you zoom the camera, because you're dealing, again, with a two-dimensional projection from rays of light to a focal point that is a two-dimensional projection of objects in a three-dimensional world. So that is a nonlinear process. You're losing information. And so if we were to look at the histogram of the wide area, well, we'll notice we have a couple peaks. We have this color histogram for red, green, and blue, representing all three color channels. You notice some of the peaks here, like this blue peak, it sort of narrows a little bit and it gets a little shorter. Now, why is that? Well, if we're zooming in, if you see this blue sky, there's more cloud, but now there's more blue. And so you're going to have a lesser representation of different values of blue as you go from the wide angle to the zoomed in version. And so this is a nonlinear process, and certainly if you're going to do feature selection based on appearance-based features for this type of problem, well, you're better off using something that recognizes or is better equipped to handle nonlinearity. And PCA is nonlinear. If you give a PCA problem a nonlinear data set, it's going to do the best it can, for better or for worse. All right, so let's also think about a manifold. We have this nonlinearity, and when we look at data, think of these data sets, and I'll first direct your attention to the frame on the right. Now, this is a set of points in the unit hypercube. Along each axis, our measurement goes from 0 to 1. Along the first axis, we'll call that the x1 axis. The second axis, we'll call that the x2 hat axis. And the third axis, the x3 hat axis. And so here we've sampled uniform at random with replacement, arbitrary points represented as some value along x1 hat, x2 hat, x3 hat. So each vector, each point here, is represented as an x vector, the ith vector, which has a component along the x1 hat axis. So we'll call that xi1. Along the x2 hat axis, we'll call it xi2. And then also along the x3 hat axis, we'll call that xi3. And so this vector xi, each one of them is some point in R3, three-dimensional real-valued space. Now, of course, if you're thinking of these data points, these three vectors, as being maybe a representation of an image, if you have an image of a particular type of object, like apples or dogs or golden retrievers or what have you, well, point clouds in feature space don't ever look like this. You don't have uniform coverage all over your space, because a particular location in feature space corresponds to a unique combination of certain colors, textures, and shapes. And so you don't have arbitrary colors and textures representing a golden retriever or an apple. It's no longer an apple. What makes a picture of an apple a picture of an apple is a unique collection, co-occurrence, if you will, of a set of colors together and a set of shapes together. And so in reality, when you look at data in feature space and real problems, it looks more like this frame on the left. Again, we have our x1 hat axis, our x2 hat axis, and we also have our x3 hat axis. Now, in reality, what happens is those points in feature space for a particular type of object don't occupy every region of feature space. They're limited to some subset of feature space. And in this particular example, these are points along the so-called unit simplex. The unit simplex is a sheet, so it's a planar surface, exists as two dimensions, and this two-dimensional sheet, it just so happens that every point is represented as a weighted sum between 0 and 1, such that the weights W1 along the x1 axis plus W2 along the x2 axis plus W3, the sum of those weights is equal to 1. That's what it means to be a point on the unit simplex. And so you can think of the unit simplex as just a special kind of feature space, and it is. And I needed to plot it. That's why I chose the unit simplex. But what I'm trying to illustrate here is that only certain values of your features, our xi vector, our 3 vector, xi1, xi2, xi3, a unique set of combinations uniquely define a particular object. So let's say you need to combine your red, green, and blue in a certain way to represent colors for an apple, or all the colors for different variations of golden retriever dogs, for example, from their images. And so what you see here is a lower dimension. This simplex is a two-dimensional shape. It's a lower dimensional so-called embedding within a higher dimensional space. So this unit simplex, all these points are in R2. It's only two-dimensional. But this lower dimensional surface in R2 occurs within a higher dimensional representation, R3. So a low dimensional embedding, it's called an embedding because it's embedded in a smaller part of your original representation in R3 for this example. Now, low dimensional embedding has a name in math. It's called a manifold. And a manifold is nothing more than a low dimensional embedding surface It could be a two-dimensional surface in R3, could be a three-dimensional surface in R4, or some arbitrary k-dimensional surface in a d-dimensional representation. And so here, in this example on the left, the unit simplex is a manifold low-dimensional embedding within R3. Okay. And so a manifold doesn't necessarily have to be one less than the dimension in which it's embedded. It can be two less, three less, four less. It can be any arbitrary subdimension. So what does this mean? This manifold means that if you're going to describe variations in certain types of data, you might not need all of the dimensions that you have available, i.e., you might not need all of the measurements or feature types. And so these are some examples of manifolds. A manifold is a nonlinear embedding, and that nonlinear part is important. Now, I know I demonstrated a simplex, but more generally, a manifold is a nonlinear embedding. It's a nonlinear embedding or low-dimensional nonlinear surface within some higher-level representational space. So these are examples of so-called nonlinear manifolds. On the left, we have a three-dimensional spline. So you can imagine like an S, right, like the letter S, and you make this S by taking a sheet of paper and just kind of wiggling it into this shape. Now, we also have on the right another called a Swiss roll. And imagine if you take a strip of paper and you sort of coil it around into this round shape. That's a Swiss roll. And the Swiss roll derives its name from the pastry. There's in the inset pictures of actual Swiss roll pastry. It's quite good. Nonetheless, if we look at the way information varies within a spline, 3D spline and Swiss roll, well, here I've drawn some axes, and these axes are going to note the direction in which features or measurement types vary. And so here we see for this 3D spline, we can go from left to right here. We see variations. It's either lighter saturation for that color or darker saturation. And then along this curved axis, if we go in one direction, we change the color. So it goes across the colors of the spectrum. We have yellow, green, blue, red, violet, green, yellow, red. So we have two directions in feature space in which measured variations in measurement types proceed. Likewise, on the Swiss roll, we similarly have these axes. We have from left to right here as a direction of change or variation, and we have this other curved axis. And so for these axes of variability, we can move along the linear, nonlinear rather, or curved surface. And so if we're going to represent points in three dimensions and they're arranged in this fashion, it's really important we understand that the variability proceeds along this curved surface in that direction. Because one of the issues that we have, let's say we have a point in feature space, this point, we call that vector x1 or xi, and we have that point, we call that vector xj. So we have xi and we have xj, and now we want to make a comparison between xi and xj. Well, if you want to see how similar they are, we said before you can use Euclidean distance. But what Euclidean distance is doing is marking this distance, the straight cut distance between xi and xj. Now, of course, if you're trying to compare xi to xq, here's xq. By this scheme, Euclidean distance measures, it's going to say xj is more similar to xi, and xq is very different, more different from xi. But the problem with this has to do with this nonlinearity, because the Euclidean measure is not the most precise measure of what difference means in this case. The reason is when you measure this distance, you're measuring it across regions of your feature space where absolutely no data exists. No data exists within this region here. but data exists across the surface. A better measurement would be to measure the distance from xi to xj by traversing across regions of feature space where data actually occurs. So if we walk along the surface, excuse me, if we walk along the surface and measure the distance we traverse or steps we take, we find that the distance between xi and xj is actually shorter, is actually longer. If we walk along the surface measuring our steps, we find that we take a longer path or traverse a longer journey. It's much further between xi and xj than it is between xi and xq. And in that regard, using the Euclidean measurement, the L2 norm, we say that xi is closer to xj, but if we walk along the surface, our nonlinear way of measuring, we say that xi is closer to xq. So that means that when you're going to measure distances to compare data expressed as points in feature space, you really want to make sure your measurements respect the curvature of the manifold along which actual values exist. Another example of this, suppose you were on the surface of the Earth and you were in the United States, and this is where my artwork goes horribly wrong, and you wanted to measure the distance between the United States and, say, someplace in China. And I'll just kind of draw a shape here, and I apologize if I'm getting the geography wrong. Now, if you wanted to measure this distance, well, one of the things you could do is actually what Euclidean measurements do is draw a straight cut measurement between, say, New York and Beijing. But what this nonlinear approach says, let's follow the so-called geodesic distance. You want to traverse actual positions of latitude and longitude in which real cities exist. And so you would take your starting point and your end point, and you go across the curvature of the surface of the Earth in order to measure that distance, where Euclidean is cutting through the ground, going through the core of the Earth to measure that distance. And you're never going to actually traverse that path through the core of the Earth. So why define your measurements in that way as well? And so this geodesic distance moves along the nonlinear or curved surface. And for nonlinear data, arrangements of data on a nonlinear manifold, it represents a much better, more accurate measurement when you're drawing comparisons between points in feature space. Okay, and so you can actually recover this low dimensional surface. You can take this 3D spline or the Swiss roll and effectively unfold it, respecting the curvature to get faithful measurements. And in essence, what that's doing is you're recovering your two-dimensional embedding, representing the pairwise relationships between points in feature space. So that means this orangish red point is going to be closer to this yellow point than it will be from that purple point down here. That's really, really important if you want to faithfully represent the relationship or similarities between your data points. So you can actually recover this low-dimensional surface, i.e. say it in 2 dimensions, by unfolding it computationally so that you can have and respect the curvature and maintain superior distance measurements when to compare arbitrary points along this manifold. And this is in contrast to the linear method PCA. And so comparing points is important for classification and for clustering, which we've seen, and we find that Euclidean measures are insufficient. As I said before, a Euclidean measure will measure the straight cut distance between 2 points. Here's our xi and our xj. Whereas taking the curvature of the surface and traversing along that path to get from xi to xj is a superior measurement. And so if we were to represent these so-called curved or geodesic distances, respecting the curvature of the measurement, geodesic, we respect the curved surface. And in our recovery, respecting the curved surface, if we can recover these axes along which variations occur, that's here, left to right, and along the curvature, we can lay out those axes as two dimensions, and we get a two-dimensional version of the relationship between pairs of points, respecting the curvature. And this is a much better measurement. So in this case, this is our measurement between xi and xj here, the yellow and the purple. Respecting the curvature, we see the circuitous path, and now we represent that longer measurement adequately along this flattened out version of the sheet. And that involves some stretching, some pulling, and some laying out, and we'll show computationally just how that is achieved. And so if you tried PCA to do a nonlinear projection on the Swiss roll, well, this is what you would get. PCA would try its best to do it, and you give it a nonlinear problem. It'll use a linear approach, our algebra, to do that, diagonalizing the covariance matrix of x transpose and the outer product. This is what you'll get. Now you notice here, it's linear. So you'll see here points that are red here in the original representation and points that are blue. Well, they're further away from one another and they traverse a long route along that curve. But as a linear method, PCA puts them right next to one another because through a linear transformation, they're very close. So here you see parts of the red right on parts of the blue. That does not respect the curvature of the original nonlinear surface. And so you can use linear methods for dimensionality reduction, but they're not going to work very well. PCA cannot capture nonlinearities. Remember from before, it does shifting, scaling, and rotation of axes. It can't do nonlinear stretching of the points or regions of your feature space along this manifold. It just can't do it. So this idea then of preserving aboutness for nonlinear data problems, it means capturing the neighborhood information. Because what makes a Swiss roll in a nonlinear fashion are the relative relationships between points and their closest points next to them, their neighbors. And so essentially what it assumes is you have locally linear structures. And so going back to that traversing the Earth example, if you're here on the Earth and you want to get from one part of the Earth to another part of the Earth, if you look within a short distance around you in some patch, you can approximate that as a straight line. And so as a series of small straight lines, you traverse along the surface. And so the assumption of non-linear paths being represented as a series of locally linear segments, you can actually approximate this nonlinear curved path quite well with small linear segments. And so the assumption then is locally along this curved surface, you have linear segments. And you can make use of that in constructing distances arbitrarily between far reaches along this curved surface and another far reach of the curved surface using a set of small linear segments between sets of points to get from one place on the Swiss roll to another. So if you do this nonlinear projection, the two-dimensional version of this nonlinear projection looks like this. And that's much more accurate in terms of preserving the local relationship. So here you have this deep red and you have this light red, and then you have this light blue. This light blue is further away from the light red than it is to the deep red. Okay. So if we look at this, so we have light red, we have deep red, we have light red, and then we have light blue. So here we have deep red, we have light red right next to it, and light blue is much further away. We're respecting the local linear facets, if you will, along this curved surface. And using these local linear facets, we can approximate a curved surface. Okay. So how are we going to do this? We effectively unroll the Swiss roll. Let's take a look at our approach. And this particular approach is called the Isomap, or isometric mapping. And so isometric mapping, or Isomap, it's a graph-based approach, and it employs a matrix of so-called geodesic distances, these locally linear segments. But where do these local linear segments come from? A geodesic means the shortest curve along the manifold. Now, of course, you don't know what the true manifold is. All you have is an approximation, and that approximation exists as your data set. So you can think of your data set as being sampled from the underlying manifold. So here, I've plotted here a sheet, and that's your actual manifold, and each one of these nodes is a data point. A data point has a projection along the X, Y, and Z direction. If you're in R3, the X1 hat, X2 hat, X3 hat axes, or measurement types. And so if we took all the data point values that you could have, that's this underlying sheet. This is your manifold. But you don't get the precise manifold. You would need an infinite number of points, or at least a very large number of points, to have a good manifold. So what you do then is that you use your data, your samples from the manifold, as a proxy, if you will, for the manifold itself. And so here you'll see edges between vertices, and these edges will connect a data point or vertex to those vertices closest by in the locally linear sense. Now, for locally linear, we're going to use Euclidean measurements locally. So here we have these straight cut distances between points, i.e. your data points, and the points closest to them. Now, fortunately, we have an algorithm in machine learning that can do this. It's called K nearest neighbor, where K is the rank that says how many neighbors that are closest to you are you going to associate with. So if K is 1, it's the nearest neighbor. If K is 2, it's the nearest 2 neighbors. And nearest is measured in a Euclidean fashion. And we can do this based on this assumption of local linearity, locally linear shape for this manifold. So we have our manifold, and we construct this graph connecting together data points or nodes that are closest to one another. And now this graph among these nodes or data points that you do have are going to be an approximation of your underlying manifold. And so what do you do for Isomap? It's a number of simple steps. The first thing you do is you take your data points and you build a neighbor graph, treating each data point in your data set as a set of nodes. You can identify the K nearest neighbors for each point using some Euclidean distance measure. That's a locally linear assumption. And then you're going to construct an adjacency matrix. This adjacency matrix is going to be used to connect each point to all of its neighbors. And so, in essence, when you think about two vertices that are not directly connected to using that locally linear assumption, let's say vertex V4, it will still have an edge to vertex V15, but it's going to take this edge between V4 and V8 and add that edge weight to this edge of V8 and V11, add that to the weight here, V11 to V5, and then lastly V5 to V15. And so each one of these edge weights, the sum of them, the first edge plus the second edge plus the third edge plus the fourth edge, that sum along the path in this nearest neighbor graph is going to be used as the distance between vertex V4 and vertex V15, even though they're not directly connected. And so we're going to construct an adjacency matrix that connects each point to every single neighbor. And then we're going to weight the edges using Euclidean distance and run a Dijkstra's algorithm, which will fill in this adjacency matrix for points that are not directly connected to one another. And so this Euclidean distance, I've shown it there, the L2 norm, and there are other distance measures that are modifications of it, like the Mahalanobis distance and all sorts of other things. But you're going to choose some Euclidean. You could insert some non-Euclidean if you choose to, but Euclidean implements this locally linear assumption. And so now you estimate the geodesic distances. And that's where Dijkstra's comes in. That's where you add up all of the paths on the nearest neighbor graph to find pairwise distances between arbitrary nodes, data points, the ith data point, and the jth data point. And this gives you, for a data set of size big N, it gives you an n by n distance matrix we're going to call D. And so you connect together nearest neighbors, you build an adjacency matrix, and then now you weight the edges using Euclidean distances between those adjacent nodes, your nearest neighbors, and then you run Dijkstra's to fill in those pairwise distances that aren't directly connected. All right, so then the next thing you do, what this gives you a distance between arbitrary pairs of nodes. And if you think about it, the distance is a form of or description of connectivity, the connectivity between nodes. Now, if you did not have edge weights, you just had a 1 for every node pairs in the graph that are connected, well, this is a connectivity, right? If you look at the number of edges that are incident to a node, that describes its connectivity, how strongly connected it is to other nodes in the graph. And so in essence, this distance matrix that we get as a result of Dijkstra's algorithm is a type of connectivity matrix, or you could also call it an affinity matrix. This connectivity tells you how strongly linked you are to other nodes, with the assumption that if you have a smaller distance, you're more strongly linked. If you have a larger distance, you're more weakly linked, you're more global. And so now we take this connectivity matrix D, this weight connectivity matrix, and we're going to construct an affinity matrix, a Gram matrix. And this Gram matrix is going to be constructed through a transformation on this connectivity distance matrix D. So what does this Gram matrix do? It's minus 1/2, okay? And so what does this negation mean? Well, this negation says, we said distances are larger if you're further away. If you negate it, that's going to be a smaller number. Now, distances are closer if you're stronger affinity, right? If you're more connected, distances are going to be smaller. So if you negate, that means that smaller distances are going to be larger numbers. So you're either going to have really large negative numbers or small negative numbers, but numerically you're going to be larger because they're going to be closer to 0. So what this negation does, it says, okay, I want to say the affinity is larger if this distance connectivity is a smaller magnitude. So you negate, essentially flipping what this distance matrix means. So then we have this transformation. We have this H that left multiplies our connectivity, and we have this H that right multiplies. So what is this H? This H takes the identity matrix, and it subtracts off the following. Here we have a vector of n1, so this is a column vector. So this is just 1, 1, 1, 1, 1, n many times. And we're going to take the outer product of this with itself. So that's times the row vector 1, 1, 1, 1, 1. And the result of that outer product is an n by n matrix. So it's n by n, and it has all ones in every row and every column. And what is that matrix? That matrix has a name. It's called the centering matrix. And how the centering matrix works, you'll notice here, I have 1 over n, and it's the average of this matrix that has all ones in it. So essentially what that gives me is a matrix with all 1 over n in every single entry. And what the centering matrix does, it's called the centering matrix, because what it does is it takes the rows or the columns of a matrix and it subtracts off the mean. It centers that linear system. So what does it mean? If you left multiply by the centering matrix, your removing the mean or centering the columns of the linear system in question. If you right multiply by the centering matrix, you're removing the mean from the rows or centering the rows of the system in question. So the centering matrix, depending on if you left multiply or right multiply, can center the column vectors of a system or center the row vectors of a system. And so here we have our centering matrix, and we're going to subtract this centering matrix off this minus this 1 over n, 1 transpose, and we're going to subtract that from identity. So what we're saying is the difference from the mean from identity. And so essentially what we're doing is we're saying when I center a linear system, I'm taking the difference between identity and that centering. And so when we think about this, that's a measurement of something called degree disparity. And it says how different is the connectivity of a particular affinity matrix when I center it out, when I center the rows and the columns, how different is it? Does it deviate from identity? And so this degree disparity, if you think about it, well, if you center everything and you're looking at the connectivity, how non-uniform is the connectivity is what the degree disparity is measuring. And so here we have our affinity matrix. And for the affinity matrix, we use this negation so that larger numbers, numerically larger numbers, or more and more positive or closer to positive, means it has a greater affinity, more strongly connected. And we divide by half because we want to scale things down. So here, you'll notice we have a left multiply for our degree disparity. So that's degree disparity for the columns because we're left multiplying. And here we have degree disparity for the rows. And the particular system for which we're calculating this degree disparity, that's going to be for our connectivity. So what it's asking then is what is the deviation from identity of the centered connectivity for the columns and for the rows? And we call that the affinity matrix. All right. And so our affinity matrix is an n by n matrix, and it involves the degree disparity for the rows and columns of our connectivity matrix. And so once we have this degree disparity, essentially what we're asking then is how similar are these nodes to one another given this linear system that measures the different ways that nodes can be related to one another, this connectivity. And so now what we enterprise to do is find the directions in which this degree disparity or deviation occurs. Because remember, when we talked about the Swiss roll, what we did is we looked at the axes in which things were related to one another, in which it varies. It varies in one direction, it varies in the other direction. And so if we took 2 points either direction, it measured between 2 points with respect to these directions of variation, how close to one another are these 2 points? Well, so what that's asking then is now that we have this degree disparity measure, we want to know in what direction does this degree disparity change. And so one of the ways we can get that direction is we can take our affinity matrix G, which is the degree disparity in the rows and the columns, and we can decompose it using Eigen Decomposition. And what this Eigen Decomposition gives us is a set of orthonormal basis vectors in the rows, that's E, And then we have the transpose of that, that's E transpose. And then we have our matrix of values, and this is the diagonal. And essentially, what this Eigen decomposition is doing is diagonalizing our affinity matrix G, this degree disparity in the columns and the rows. And it'll give us the rows of this E vector. It'll give us the set of measurement types, our axes, if you will, or bases, that describe the directions in which degree disparity varies or changes. And so we're left with a set of eigenvectors, big N of them, but we don't need all N of them. We're going to choose some K of them, and the K that we choose are going to be those K eigenvectors associated with the K biggest diagonal terms. So we're going to have V1, V2 along the diagonals up to Vn, and there's going to be some Vk such that the variability in our data set is explained by a significant amount, typically 95%. Okay, and so these eigenvectors are associated with the eigenvalues, and the eigenvalues describe the variance or the amount of affinity or degree disparity in each one of the directions described by these eigenvectors. And so you take the top K eigenvalues and their associated vectors, and you use those vectors with the original representation to project the original representation onto those K many eigenvectors to get your new version of the data set. And now these K eigenvectors will describe the axes that respect the geodesic distances between points. And so we figured out what the affinity was, the degree disparity. That's how the affinity varies. And we diagonalized that system describing the degree disparity, how the affinity varies. And we decomposed it into diagonals to find the directions in which those values, the affinity varies. And so we take the top K eigenvectors and values, and then we project the original data set in 3 dimensions on our nonlinear manifold, and we get back a reduced version that respects the geodesic distances. All right, so with that, that is the Isomap algorithm. Please make sure you're reading through all of the links that I have. I put them on the course Blackboard. Next time, we'll continue with more ways of doing these nonlinear feature selection methods. Until then, I will see you Thursday. Please stay healthy, stay safe. I'll see you Thursday.